Okay. So, in the last lecture we have started the Cantor's theory of irrational numbers, and in fact, this is another way of introducing the concepts of the real number, which is entirely different than the date kinds had done it. So, here with the help of the convergent sequences of a rational number, Cantor has introduced the concept of the rational and the irrational points, and then he later on we will we will show that basically these two approach are basically equivalent, they are not a different. Okay, different. So, yesterday we discussed about the convergence part of the rational numbers, convergence sequence of the rational number and various property. So, let us just recollect a sequence n of rational numbers is said to be convergent if for a given positive small rational number epsilon, any positive small rational number epsilon, there exists for a given positive rational there exists an integer and not positive integer such that the difference between a n plus p minus a n naught plus p minus a n naught remains less than epsilon for all p is 1, 2, 3 and so on. Then such a sequence a n of rational number is said to be a convergent sequence. It means that after a certain stage, if these are the points a 1, a 2, a 3, a n naught plus 1 and so on, this is a sequence of rational number. The sequence will be convergent if we assign some positive number, given any positive number epsilon small, corresponding to this epsilon, one can identify n naught. It means the n naught will depend on this epsilon, such that if I truncate this series, then after this all the terms of the sequence will satisfy this condition. So, difference from a naught to any other term can be made as small as we please. For example, suppose I take a n's to be 1 by n, a sequence of rational number, we say it converges to 0. It is a convergent sequence because take any epsilon, say epsilon is 10 to the power 10, then corresponding to this epsilon one can find a n naught such that mod of a n naught minus a n naught plus p less than epsilon means 1 by 10 to the power 10, is it not? And that will be equal to what? This is 1 by n naught minus 1 by n naught plus p. This remains less than 1 by 10 to the power 10. Okay. If I simplify this part, then what you get basically? This is nothing but what? N naught plus p, and then p over this part is less than this, clear? P is also positive. So, this is less than. Now, this entire thing p over n naught plus p we can already find from here. Suppose I take p equal to say 1 or 2 anything, then from here we can write 1 by n naught, let it be n naught plus p to be say m. So, m is greater than n naught when p is greater. So, m is greater than n naught, then this becomes n naught m, and then p you can just write p is 1, 2, 3. So, we can say p is less than 1 by 10 to the power 10. Therefore, n naught into m divided by p is greater than 10 to the power 10. So, m can be obtained. So, from here m will be greater than 10 to the power 10 into p by n naught, is it not? So, corresponding to this n naught, this number, if I choose this number, all the terms which are greater than this number will satisfy this condition, is it not? Will satisfy this condition. It means you can easily find out the truncate the series where this happens. Okay. So, we can get it this not fixed like this. This can also be said equivalently this part when we say such then this is a or equivalently here as a or equivalently we can say that for a given epsilon greater than 0, one can find a integer n naught such that mod of a n minus a m less than epsilon for all n m greater than equal to n naught. Both are equivalent. So, either we can use this or we can use this that one. So, that was the first. Then we have already seen that if a sequence is a convergent sequence of rational number, then it must be a bounded sequence, and the terms of this sequence we can find out the two a n plus p, which can lie between a n naught minus epsilon and a n naught plus epsilon that part. So, this one. Then there are certain properties of the, if suppose there are two sequences, various properties, the addition, multiplication and subtraction, let a n and b n be two convergent sequences of rational numbers. Rational numbers, okay, rational numbers. Then one a n plus minus b n, this new sequence, may addition of the two sequence or subtraction of sequence is also convergent. Product of the two sequences a n into b n is also a convergent sequence. The division of the two sequences a n divided by b n is also convergent, provided the sequence b n, provided all the elements of the sequence b n are numerically greater than some fixed positive number k. Positive number k. Okay. We have already checked the first one, this already proved with the epsilon and delta. The proof of this, let us see the others. This one already done yesterday, so no point of repeating the whole thing. Let us see. We wanted to show if a and b n are the two convergent sequence of rational number, then their product will also be a convergent. It means we wanted to check basically this condition, a n naught minus a n naught plus p, it means less than epsilon for this. So, instead of this a n naught, we will say a n naught b n naught, a n naught plus p, b n naught plus p. If this remains less than epsilon for given, then we can say it is okay. So, construct a sequence, consider the difference mod of a n b n minus a n plus p b n plus p. Consider this difference. Okay. And for p is equal to 1, 2, 3 and so on. Now, this can be written as a n b n minus b n plus p plus b n plus p into a n minus a n plus p. Just adding and subtracting this term a n into b n plus p and get it. Now, this is less than equal to mod of a n into mod of b n minus b n plus p plus mod of b n plus p into mod of a n minus a n plus p. Is it not? Just modulus sign, because mod of x 1 plus x 2 is less than mod x 1 plus mod x 2. Now, since a n is a convergent sequence, so according to that every convergent sequence is a bounded sequence. Similarly, V n is a convergent sequence, so this has to be bounded. So, since a n and b n's are convergent sequences, so they are bounded. So, they are bounded sequence, bounded, that is there exist alpha beta, there exists some alpha greater than 0, beta greater than 0, such that all the terms of the sequence mod a n is less than alpha and mod b n is less than beta for n, all n, for all n, for all n. Every convergent sequence is bounded sequence. So, this happens. So, we can find alpha and beta such that this. Now, further b n and a n are convergent sequence. So, we will make the criteria from here. Okay. So, we can get from here is therefore, mod of a n b n minus a n plus p b n plus p. This is less than equal to alpha times mod b n minus b n plus p plus beta times mod a n minus a n plus p. Okay. This is okay. Now, since a and b n are convergent, so for any given arbitrary small positive number epsilon, one can find a common n. So, that this can be made as small as we please and this can also be made as small as. So, since a n and b n are convergent, so for given epsilon greater than 0, a small positive rational number, one can find an n, an integer n naught or n naught such that mod of b n minus b n plus p remains less than epsilon over say alpha plus beta, and mod of n minus n plus p remains less than epsilon by alpha plus beta for all n. Okay. So, this is true a naught I have write for all n, this can be okay. For n we can find an n such that this holds. So, instead of n naught we can say just n, okay, or let n naught, where the p is 1, 2, 3 and so on, okay, by definition. Clear? Now, again pick up from 1, this is 1. So, from 1 what we get, a n naught b n naught minus a n naught plus p b n naught plus p is less than equal to alpha times b n naught minus b n naught plus p plus beta times mod a n naught minus a n naught plus p. Change n to n naught. So, that it is true for p 1, 2, 3 and so on. Now, this is less than, so this will remain less than alpha into epsilon y alpha plus beta. This is also less than beta into epsilon over alpha plus beta, which is equal to epsilon. So, this is true for all p starting from 1 to n so on. So, this implies that sequence a n b n is a convergent sequence. Convergent sequence. Okay. So, product of the two sequence convergent sequence is convergent. Clear? Clear? So, this is the proof for the part 2. Clear? Part 2. Now, proof for part 3. Proof. We will show that division is also, if the two convergent sequences are there, then one can divide a n by b n provided the b n is greater than 0 or greater than all the terms are greater than some positive constant k, then the a n over b n is also a convergent sequence. So, let us start with this division. So, what we use again in a similar way we start with this. So, consider say mod of or a n by b n minus a n plus b over b n plus b. Consider this. So, what is the mode of this? Now, this we can write it as a n b n plus p minus b n a n plus p over b n plus p, mode of this. And now, again you break up in the form. So, what we get it? This is basically equal to a n b n plus p minus b n and then plus b n a n plus a n minus a n plus p divided by mod of b n mod of b n plus p, is it not? That is what is. Now, further this is less than equal to mod of this and there. Achha. Now, it is given that b n, since each term of the sequence b n is greater than, numerically greater than or equal to k, this is given. Okay. So, we can say that mod of a n over b n minus a n plus p over b n plus p is less than equal to mod of a n into mod of b n plus p minus b n plus mod of b n into mod of a n minus a n plus p divided by mod of b n plus p. Okay. Now, this is given and sequence a n and b n are convergent. So, bounded. So, bounded. Therefore, there exists a alpha and beta. So, that mod a n is less than alpha, mod b n is less than alpha. So, this is less than equal to alpha times b n plus p minus b n plus beta times mod n minus n plus p, and since b n is greater than mod b n. So, 1 by b n is less than equal to 1 by k. So, this is k square, where mod of a n is less than equal to alpha, mod of b n is less than equal to beta, where alpha and beta both are positive quantity because of the boundedness. Okay. So, bounded. Now, pick up the epsilon. So, for a given epsilon greater than 0, let it be this equation 2. Okay. For given epsilon greater than 0, which is a small positive rational number, one can find an integer n naught such that this thing is less than, suitably less than epsilon or something, and this is also a small quantity. So, we can say that mod of b n naught plus p minus b n naught is less than alpha over alpha plus beta, and then k square we want to remove. So, let it be removed, sorry, this is epsilon not alpha, this is epsilon. So, epsilon into k square epsilon into k square by alpha plus beta, and mod of a n naught minus a n naught plus p is also less than epsilon into k square divided by alpha, because basically this is very small quantity. Once you multiply by epsilon, the whole thing becomes very small. So, n naught can be chosen in such a way, so that this entire thing is less than this, similarly this less. Substitute this into, so put it into. So, what we get is a n naught b n naught minus a n naught plus p over b n naught plus p, change n to n naught. Then we get this is less than equal to alpha. When you write this thing, you are getting epsilon by k square, epsilon into k square by alpha plus beta. This is also beta epsilon k square by alpha plus beta and divide by k square. So, finally, what you get, k square get cancelled, alpha plus beta get cancelled, and finally, you are getting what, epsilon only, and this is true for all p equal to 1, 2, 3. Therefore, the sequence a n y b n is a convergent sequence, is convergent sequence of rational number. Okay. This is what we get. Is it okay? Now, after developing this thing, Cantor was able to introduce the concept of real numbers. So, what is the Cantor's theory of real numbers? Yes, you wanted something?
No.
Okay. Cut. But why it is cut? I think it's yes drawn. Huh? No. Yeah. थोड़ा ऊपर इसको लाना है. Okay. So, Cantor's theory of real numbers. Okay, what is the Cantor's theory? The Cantor theory postulates the existence of a set, infinite set of object, which we call it as a real number. So, Cantor's theory postulates the existence of a set of object, infinite set of object, of course, set of object, which called infinite set of object, which is called real numbers. And every object of this set is associated with a convergent sequence of the rational number, and any element of this set, is supposed to be symbolically represented by means of a convergent sequence of rational numbers. Convergent sequence of rational numbers. It means what is the meaning of this is that what the Cantor said, that if we pick up any convergent sequence, any sequence of the rational number which is convergent, then this sequence will converge either to a rational number or to a number which is different from rational, that is we call it, that they call it a irrational number. So, every convergent sequence of rational numbers will gives every convergent sequence of rational number gives either a rational number or irrational number. Which are not rational, they call it as irrational number. Convergent part means every sequence, convergent sequence of the real number, this there will be every convergent sequence of rational number defines a real number which is rational or irrational, and converse is also true. Conversely, any real number is defined by means of a convergent sequence of rational number. A convergent sequence of real numbers of rational convergent sequence of rational numbers. So, this is the theory given by Cantor, and this is known as the Cantor's theory of real numbers. So, what is his postulate is? What he says is that if we have a class of the objects which we call it as a real number, then any real number if you picked up, then corresponding to the real number we can identify a sequence of the rational number which will converge to that point. If it is rational, then the limit point is called the rational reals. If it is not rational, then we call it irrational, but the convergent sequence we can identify. And conversely, if we are having a convergent sequence of the real number or set of the real number, then every convergent sequence of the real number will give a real convergent sequence of the rational number will give a number which is either a rational or a irrational. So, there is a correspondence between the set of real number and set of the convergent sequence of rational. This is the set of real number, and here is the set of convergent sequence of rational. Pick up any alpha, corresponding to this we can identify a sequence x n which will converge to this and vice versa. Okay. Now, if we pick up any sequence, we can find out here the number this. So, like this. Okay. This theory is given by Cantor, but there is a very simple way he has introduced. Dedekind had introduced in a very complicated way. What he did, he has considered the objects of the points and then introduced the sections and then lower class, upper class, and then finally he got that rational number and irrational number, like that. So, he had developed the three type of the classes and then introduced, but here simply in the form of the convergent sequences he has introduced the concept of rational and irrational number. But what is the drawback? Main drawback in this is that a real number, if I picked up a real number, then there are many sequences of rational point which will converge to the same real number.
There may be
many sequences
converging the same point.
Infinitely many we can find out. This is the drawback. The drawback of this is the drawback of this theory is that the drawback of this theory is that it does not explicitly express any single number. For example, suppose I take the sequence say 1, I choose the number 1, then 1 will correspond to this sequence say 1, 1 minus half, 1 minus 1 by 3, 1 minus 1 by 4 and so on. That is 1 minus 1 by n, this sequence will go to 1. But on the other hand, this will also go 1 plus half, 1 plus 1/3, 1 plus 1 by 4 and so on. This will also 1 plus 1 by n, this sequence will also go to 1. So, there are many finite sequences are available which can go to the 1. In fact, any real number you picked up. Similarly, for irrational also, it is not for irrational only one sequence. There are many sequences of rational which can be generated and whose limit point is the rational number given. So, this is the main drawback. But if we look that finally, in spite of this drawback, both the theory are equivalent, both the theory gives the equivalent concept and both are equivalent basically. They are not generating an extra element which is not available in the first case. Means there also we are getting a continuum, the entire real line, with the help of this also we are getting a continuum. And just like as previous case, when we apply the Dedekind theory for sections cuts over the set of real number, we are not getting a further extension. Similarly, here also when you apply the Cantor's theory of sequences over that set of real numbers, set of sequences of real number, you are not getting a further generalized further extension. So, basically we are not getting a new thing, both are equivalent. Okay. So, that is the what you say. Is it clear? Now, there are certain relations like how to define the two sequences, two elements are equal, one element is greater than other or less than other in the form of the in this Cantor's way. So, let us see some to define A is greater than B, A is equal to B, A is less than B, where A and B are real numbers. Suppose we how to define it? Let us suppose let sequence A n and B n be the two convergent sequences of rational numbers which represent the number, the real number A and B respectively. Suppose we have the two sequences, convergent sequence of the rational number which represent the real number A and B. Then we say number 1, we say A is equal to B, we say the number A is equal to B, the numbers A and B are equal if for a given epsilon r greater than 0, for given epsilon r greater than 0 rational number is small, okay. For a given epsilon greater than 0, there exists a positive integer, there exists an integer n such that mod of a n plus p minus b n plus p is less than epsilon for p equal to 1 to 3 and so on. Okay. For p 0 obviously 2 there is no problem, for 1 to 3 then we say the two sequences, two real numbers are equal, means the number represented by this sequence, number represented by this sequence are basically equal number. For a given, so for example, if I take these two sequences, for example, if I take the sequence 1 minus 1 by n, this sequence and the sequence 1 plus 1 by n. Okay. This is our sequence A n, this is a sequence B n. Now, they represent the same number 1 and this is also 1. So, basically this is say A, this is say B. We say A is equal to B. What if the difference between the terms of the sequence after a certain stage can be made as small as we please. So, if I take any epsilon greater than 0, choose any epsilon greater than 0, howsoever small may be, howsoever small. Then what is this? Difference of this will be n plus b minus b, means it is basically what difference? The difference will come out to be 2 by n only. The difference of this will come out to be 2 by n. It can be made less than epsilon. So, n must be greater than what? N by 2 is a 2 by epsilon. So, after this stage we get all the terms of the sequence are basically very small, very close to each other, very close. So, though that sequence looks like a different sequence, we are not saying these two sequences are identically equal. We are not saying that sequence A and B n are equal sequence. We are not saying this. What we are saying is the corresponding limits are equal, corresponding limits are, because when the two sequences are said to be equal, when they have a corresponding elements are equal. Okay. So, that we are not saying by, because two sequences are equal, obviously they will represent the same point. No, but since here in Cantor's theory a point can be represented by many convergent sequences. So, how to define that two limit point to be equal? We said they are equal when, only when these two sequences which are different, but their behavior after a certain stage is within our limit. That is, the difference is very negligible, very almost equal to 0 when n is sufficiently large. Then we say these 2 points, these limit points are equal. Is it okay? That is one. In fact, it will go to 0 when n is sufficiently large, difference will go to basically 0. Now, similarly we say that is second. Not that. Okay. Similarly, we say second part, the number A is greater than B. If a value of n can be found, if an integer n can be found such that a n plus p minus b n plus p, this difference for p is 1, 2, 3 and so on is greater than some fixed positive rational number delta, some fixed positive rational number delta. Okay. Means whenever this n plus p minus n is greater than some positive rational number delta, then we say the sequence A, the number A is greater than B. Now, if n can be so determined that the difference is negative, that the difference A n plus p minus b n plus p is negative, but numerically greater than some fixed positive number, numerically and numerically greater than means without sign, numerically greater than some fixed positive rational number delta, then the number A state, then we say the number A is less than P. Okay. And when equal, we have already discussed. So, given any sequence, two convergent sequence which represents the number A and B, then one can also identify the ordering between them by seeing this thing. So, this way he has introduced the ordering between the two real numbers. Okay. Now, if we take this two sequences A n and B n, then whether this A n and B n they are okay. Positive, negative, positive, negative and this positive, negative and 0 number. Zero real numbers. Positive real number, in a similar way we can define 0 number when mod A n plus p, except 0 number when the mod of A n plus p is less than epsilon. Okay. For certain n greater than there, for given epsilon we can find a n such that this is true for all p. Then we say the sequence of this A n are basically going to 0. Why mod is there? Because there is a chance of getting the 0 from the negative side, chance of 0 getting the negative side. It means the elements, some elements may be positive, some may be negative, it may go alternately positive negative, but it approaches to 0. For example, if I take minus 1 to the power n, then what happens? It goes the plus 1 minus 1 plus 1 minus 1, but the limit of this is tending to 0. So, in this case when the terms corresponding to 0 or when it tending to 0, the sign of the n plus p may vary, but when you take the positive or negativeness, then what happens is when you say the positive, it means after a certain stage a n plus p must be greater than 0, must be greater than 0 for p 1, 2, 3. So, after a certain stage the terms may be negative, they are negative here, but after a certain stage all the terms should be positive. Then only we say that the number which is represented by this sequence will be a positive number. When the sequence is given, some terms are negative and some are positive, but when n is sufficiently large, the terms are going to be positive. So, the limiting point will be a positive quantity, will represent a positive real number, but in otherwise if we take the few terms are positive, but rest are negative, and when n is sufficiently large, the terms are coming to be negative, the limiting point will be a negative. So, in that case we say the real number is negative. Okay. So, that is what we are saying. Okay. Next is our the sum difference and the product is defined like this a and b n. So, that is not a problem. Now, as we have seen that the if a n and b n are the two sequences are convergent sequences of rational numbers, let a and b n be convergent sequences or convergent sequence of rational numbers, representing suppose representing real numbers a and b respectively. Okay. Clear? Now, if I take, since these are not only the representation, but suppose a dash and n dash, a n dash and b n dash be another sequence, another convergent sequence of rational numbers representing the real numbers a and b. Now, question is will sequence a n plus b n okay, all a n minus b n and a n dash plus minus b n dash will give a plus b or a minus b. This is a one set of the sequence, a n converges to a, b n converges to b. Then we are finding a n plus b n, limiting behavior of this will be a plus b. If we take minus, then it will be a minus b. Now, what I am claiming is, in place of a n b n, I am choosing a n dash and b n dash, which are the sequences also converging to a n b. Then instead of a n plus b n, if I take a n dash and b n dash, whether this sequence convergent sequence will represent the same sum as the sum of this sequence. Similarly, if the product a n b n and product a n dash b n dash will give the same number a into b. That is what is there. Otherwise, if it gives a different, then the entire theory will be fluffed. There is no point of developing the theory in such a way. So, the answer is yes. Similarly, a n by b n, where the b n is not equal to 0 of course, and a n dash over b n dash, where the b n dash is not equal to 0, will give the a by b. So, these are the answers question. The answer is yes. Okay. Let us verify one and then we will see. Okay. So, suppose I take 1. Okay. So, let us consider mod of a n plus p plus b n plus p or minus also minus a dash n plus p minus plus b dash n plus p or minus sign, both I am taking at a time, plus and minus. Now, this will be less than equal to mod of a n plus p minus a dash n plus p, okay, plus b n plus p minus b dash n plus p, because minus will not affect much, okay, when minus minus plus and become. Now, what is given? A n and a n dash represent the same number a. So, by definition, the way he has introduced the number a, if it is represented by two different sequences, then basically after a certain stage the difference can be made as small as we please. So, since these sequences represent the same number, so this difference can be made as small as we please, say epsilon by 2. Similarly, this difference can be made as epsilon as please, epsilon by 2. So, total is epsilon for all p, for p equal to 1 to 3. So, what this shows? That this difference is less than epsilon, it means this sequence a n plus b n and a dash n plus p, b dash n plus p will give the same number, and that number is nothing but a plus b. Similarly, for the difference, is it okay? And the same trick, same case you can use for the verification for the product. Product of these two will the similar way we can write. For the product, if you write a n plus p, b n plus p minus a dash n plus p, b dash n plus p, then this is less than equal to a n plus p mod of this, mod of b n plus p minus b n, and then b n dash or dash b n dash plus p, sorry, this is plus p, okay. Then plus b dash n plus p mod of a n plus p minus a dash n plus p, just breaking, adding. Now, again these are bounded because these are convergent sequence. So, this is less than equal to alpha into mod b n plus p minus b dash n plus p, and this is beta mod of a n plus p minus a dash n plus p. Okay. Now, again this b n and b dash n represent the same number. So, it can be made as small as we please. So, I can make this thing is epsilon by alpha plus beta by, is it not? And this also, because it is also a small same sequence. So, after certain step we can make it to be epsilon by alpha plus beta for all p 1 to 3, but this is epsilon. So, this is true for all p 1 to 3. Therefore, these two sequence basically give the same number, that is a. Similarly, the also we can justify. So, what we say that these properties are satisfied with them. Similarly, associative property, commutative property etcetera can be justified in by with the help of the Cantor's theory, that is the limit of the sequence of convergence term. Now, here one more the indices can also be generated defined in terms of the sequence of rational numbers in terms of the sequence. So, this is our indices. What is that? Suppose I take x be a case 1, let a be a alpha is a positive integer, let alpha be a positive integer, yeah, alpha be a positive integer and x be a real number represented by a convergence sequence x n of real numbers Okay. Then x to the power alpha, this number, this is also a real number, will be represented by sequence x n to the power alpha. This is the way he has into. Suppose alpha be any positive integer and x be a real number which is represented by x n. So, x to the power alpha will be represented by a sequence x n to the power alpha of rational points. These are the rational numbers, is it not? X n is also any integral power will also be rational. Similarly, if alpha be a fraction, be a rational number, say p by q, then x to the power alpha will be is represented by x n to the power p by q. This sequence x to the power alpha is represented by x n to the power p by q, and where x n sequence converges to x. Now, only here the difference is, since q, this square root of this here, notice the x to the power 1 by q, qth root is valid only for when x is positive, or q is x, or if q is odd and x is negative, and x is negative.
Sir, case 1 and case 2 is very similar. Basically,
alpha is integer and here it is rational. So, p is integer, but 1 by q I am talking. 1 by q, because this is not, this is defined for even that x n be a say negatives, but here x n cannot be negative unless if x n is negative, q has to be a odd numbers, then only it is defined. So, for irrational case we will see later on. Thank you very much. Okay. Next class we will see.